Well, let me begin by thanking the organizer for this opportunity. Today I'm going to talk about particle correlation observed in UPC and LHC. So let us begin by staring at this two-particle correlation plot from Atlas collaboration. So in this plot, what was plotted is the distribution of the two particle pairs in terms of their azimuthal angle difference and their rapidity separation. In some literature, this was called ridge correlation because this correlation persists in the rapidity direction. It looks like a ridge of a mountain. Now, in this work, we want to focus on the angular correlation. So in the theoretical calculation, what we've done is we take a slice and focus on one rapidity separation. But as a demonstration, if we want to focus on the angular correlation, in the same paper, Atlas demonstrated an example about how do you extract signal from the data. So let's look at this solid red curve first. So this is high multiplicity data, the fit of the high multiplicity data, which include the background and the signal. And we know that low multiplicity data is mostly the background. So there is this template to rescale the low multiplicity data, and then you subtract it from the high multiplicity data. What you see from their difference is these two curves. Those are the flow signals.
What is the units and the angle?
Yeah, units is angle.
No, but what are the units and the angle?
It's typically from 0 to 2 pi, right? But
Yeah,
the unit number.
Oh,
Radius.
it's radius.
Yes.
So these are back-to-back correlations. They're not.
There's a strong back-to-back background. But we're
background.
Yes. So like after the separation, if you zoom in, you see that at 0 and pi, they have equal minus correlation. So that's what we're looking for in this calculation.
You're looking for the collective
Yes.
part.
I want to focus on V2 here. All right. So let me give a simple introduction to the V2, which has been discussed by many speakers. So in the heavy ion collision, right, it's highly likely that the particle is not head-on collision. So it has this almond-shaped intersection. As a result, let's say this is y direction, this is x direction. The pressure in the x direction is greater than the pressure in the y direction. So the particles will prefer flow in the x direction, either the same direction or back to back. One of the major application of this flow signal is to measure the viscosity of covalent plasma. So basically, if you start with the same amount of correlation as the initial condition, and then if the fluid has higher viscosity, you will have less correlation survive in the final state. So then you just tune this viscosity in your hydrodynamic evolution, and then you feed the data to see what the viscosity of the fluid. So this is just to remind us the definition of this fluid coefficients is just the harmonics of our harmonic coefficients of our cross section. Now we can take this step further and ask question. So how far we can push this paradigm to study the collective behavior in the collisions, right? So we can go to smaller system. I think the first small system flow was observed in the CMS, I think high multiplicity proton-proton collision. And then there was a serious experiment was done in LHC and ring. Now, in addition to that, we can also ask if there is other mechanism that can contribute to similar signal. Right, so on the one hand, it's certainly complicating your analysis. On the other hand, it also opens new opportunity to probe some new effects. Now, if we go to extreme condition, right, the smallest projectile is a DIS photon. We can go to like Q square as higher as possible, as permitted by the experiment. Now, we don't have the electron ion collider yet, but we do have a prototype, which is the photon nuclear interaction from UPC. So UPC refers to the events when, in your heavy ion collision, when the impact parameter is greater than the sum of the radius of the two heavy nucleus. In such case, we can use the so-called equivalent photon approximation. Now, the physics picture is that if you think about a rest nucleus, it's basically a charge emitting Coulomb field. But when you boost this electric field, what happens is that the longitudinal direction field was heavily suppressed due to the Lorentz contraction. And then you effectively end up with a two-dimensional transverse field. So we can approximate this field by photon flux. So in some literature, this photon field was called Weizsäcker-Williams field. As a small digression, right? So if we this is related to how we model nucleus. So if we replace this charge, electric charge, with a color charge, then we can also have Duan Weizsäcker-Williams. All right, that's a small digression. We will talk about this later. But there are certain complications from this UPC photon, is because the photon was emitted by the nucleus coherently. So basically, you can think this way: the photon will not be able to resolve the small structure. So the Q square of this photon was bounded by the size of the nucleus. So as a reference, for atomic number greater than 16, the Q is about 60 MeV. So it's like way below the lambda QCD. So this system itself is not perturbed, and we need to do some modeling. Now, before we go to the details of the theoretical discussion, I just want to point out that there's several discussion study has done for this correlation in UPC. The first one is that we still treat this as a hydrodynamic system, and it was done by Trinchen and beyond their problems. People can ask them about details of their work. The second one is the so-called color domain effect in the target. Now, a simple picture is that think of nucleus as a piece of magnets. So inside the magnets, you have those domains, right? So in their study, they think of like when you have two gluons, they hit the same domain, they will be correlated. But in our calculation, the correlation due to the target effect was actually subleading. Now, here I want to focus on the discussion of quantum correlations inside the projectile. There are two types of correlations in the projectile. First one is Bose-Einstein correlation. So because gluons are bosons. The second one is HBT effect. Is due to like the source of the emission is not like important particle, but it's extending source, and we will have fluctuations. As a simple demonstration, how this correlation arises from the two-particle correlator of a free boson gas. So if we measure this correlator for two boson, we have essentially three types of different scenarios. First one is that they contract with themselves, right? A contract with A, B contract B, think of this A, B as a color index. And the system is uncorrelated. If we denote this part as of order 1, then we also have so-called round contraction. So you have one lot less color index, and this term will be suppressed by 1 over n². All right, and the one last contribution is that when all this momentum is the same. But when all this momentum is the same, this contribution is further suppressed by the phase space volume, which is subleading. So here we only focus on this correlation. Now, HBT was originally used in astrophysics to study the size of the star. But here, I only want to emphasize that the correlation arises because you have the round contraction of the color index. So instead, due to the both statistics, this round contraction can also be enforced by the ensemble of your ensemble average of the source, and it gave rise to a rather strong peak in the angular direction. Right. So after all this introduction, I want to describe how this theoretical study was set up. So first step, we need to model the projectile. So we need some model. And we sampled a source from some distribution as a starting point. Then from this source, we create 1 or 2 gluons. Here I only show 1. And the gluons and the source will go through diagonal scattering. They will pick up a phase and their color rotated, and they got a transverse momentum kick. And then they pass through this final state cut. Then we can compute observables. After we have expression for the cross section, we do the ensemble average, which is essentially that we have to, take into account all possible configuration for your projectile and for the nucleus. Then we analyze what is background and what is single.
So this is just single particle distribution.
This is a demonstration. So like you can have 2 more particles, but it will take too much space. So the first step is the photon. Now, because it's non-preservative, we don't really know like what's going on. What we did is that we take 2 extreme limits of the photon. So the first one is the dilute limit, where you only have this, split of the quark and anti-quark dipole. And you want to see how, if there are any correlation just from this very dilute system. Because the Q² is small, so the longitudinal polarization is strongly expressed, and you only have a transverse polarization here. Also, the advantage using the dipole model is that the expression we got from this calculation can be very easily sent to EIC kinetics. Another model is the so-called MV model. MV model is essentially you're treating this photon, non-perturbative photon, as a hadron, because photon is a vector particle, so its hadronic component can fluctuate into other hadronic system with the same symmetry. So the closest one is like a vector method. Right? Now we don't exactly use this model, but we know that the system can be treated as a dense gluonic system. So what we did is like we sampled this the source of the soft gluon from the distribution function, which is Gaussian. Now, why this is Gaussian is actually have a simple way to see this. Imagine you have a bunch of electric charge and you add them together, you just get a bigger number. But if you go to for example, like SU2 charges, you're adding a bunch of spins. Now things become non-trivial because if you have one spin, you have two direction, right? You have two spin, it can go either way. So it looks like a random walk in the z direction, right? So for SU2 charges, you can actually show that the average fluctuation of this charge density is satisfy this Gaussian distribution. For SU3 charges, it has been shown that it is a Gaussian distribution plus a small correction. So it's certainly like justified in certain regime that we can use this Gaussian distribution to sample the so-called valence degrees of frequency.
It's a Gaussian fluctuation in the color space, or also in both color and let's see momentum space, or
Yeah, so like in coordinate space, you can start with coordinate space, and then there are diagonals in color space. I don't think you.
because you mentioned SU2, so you need even in the skin, they will randomly flip skin and
Yeah,
randomly change color.
yeah,
But usually in MV, it's Gaussian and everything.
Yeah, everything.
Rigidity and transfer position and it's color.
but you can also introduce like the non-trivial dependence to this mean square.
Yeah.
Now, after we sample this source, we create some gluons from this source. The way we do this is, by the way, you can do this in a rigorous way, which is like on perturbation theory, and take care of everything like step by step. But here, if we only consider like very few gluons, we can do it. We can create gluons using this coherent operator. So this operator, which is basically a generalization of the current coherent state in quantum optics. So this A and A dagger will create your gluon field, and this B field is you can think of it as an amplitude of the classic gluon field given by this source. And this formalism is rather general because if this operator acts on a MV model source, it's gonna create gluon based on MV model. If it act on this quark anti-quark dipole localized in transverse coordinate space, then it's gonna create gluon based on this source. Now, if you want to create gluon from another gluon, then this operator will act on a gluon with higher rapidity, and it's going to create, a gluon at lower rapidity.
But the MV model doesn't it already have a whole ton of glue?
Hmm?
The MV model will give you already a whole many gluons, right?
Yeah.
Or is this just how you generate those standard gluons of the MV? We're trying to compare the two cases, right? In the one case, we just start with dipole, right?
Yeah.
To emit glue, right?
Yes.
And in the other case, would you start with gluon color charges, right?
Yeah.
Is that what you mean? And then you generate the field from that.
Yeah.
Okay.
Now, after you create two gluons from the system, they will go through the shock wave, which is our model for having nucleus. They will pick up a phase vector, but there's no recoil because it's the scattering is axial. So in our calculation, of course, I want to mention that the strong field is a functional of the valence source in the target. It's not. This target was modeled in a similar way as an MV model, but with fewer complications. Now, in our calculation, after certain approximation, the only thing we used for the target degrees of freedom is this dipole operator, which the only thing that The only phenomenologic parameter is this saturation momentum of the target. Now the cross section, things start getting a little bit messy, but I want to explain a few important points. So the first one is that the result is a cross section in the momentum space. And this sigma is the matrix element in the coordinate space. Now the way we do this is that we start by an initial state, right? You have the photon wave function based on your model. This coherent operator has two components. So this B operator will act on this initial state photon wave function. And this A operator will act on the coherent gluon vacuum. So you start with nothing, and with this guy act on the vacuum, you get one gluon. Now, because we have two gluon, we have to take into account the possibility that the higher rapidity gluon can emit another gluon, which is this second operator, right? We're taking this rapidity to be smaller than beta, right? So the source term for this lower rapidity gluon consider two contributions. One is the original source, the other one is the first gluon. So after you create this initial state, they go through agonal scattering, and then you observe your two gluon in the final state. Now the final state gluons stressed by even softer gluon. In the leading order, this might not seem like an issue, but if you go to high order, you have to take this into account with cancel certain to take into account certain virtue contributions.
Sorry, the whole target information is in the S matrix.
Yes.
Okay.
Now we will not do any like detailed calculation. Now I want to organize. So, but there's still some physics we can extract from the simple diagrams. So the first one is we can organize the cross section coordinate. Sigma is a coordinate space matrix element according to the power of this rho. Right. So it is natural to expect that this rho to the fourth term corresponds to higher multiplicity events. And this rho square and rho cubic term is lower multiplicity events. Later, I will explain why these terms, the first two are the background, how we separate the signal from the sigma 4. Now, as a demonstration, so the expression for this matrix element has three components, right? You have some bunch of iconal green functions. Those are just iconal emission vertex. And then you have the projectile average, right? For now, I haven't used any model yet. And we have sigma 3 or sigma 4, you just have like 3 row correlators, 4 row correlators. It is very nice that all of our target average can be expressed in terms of a 4 Wilson line correlator. So after we go to momentum space, all of them are simplified. Now,
Just one question, the diagram that you saw in the previous slide. So the right one will have more combinations of diagrams, right? It's just one such.
what do you mean right one?
So there's one which is from two different particles. No, the right.
C.
Yeah, this one. You will have more combinations, right? Like 9 different ways to combine it. Is this the only diagram?
Oh, no. This is a demonstration.
Oh,
yeah,
okay,
yeah.
good.
Now we take the expectation value for the projectile and target. Now we start like using the models. Now for the dipole, the first step is we take the average because we know the expression of this rho, right? And we know that we have two quark anti-quark dipole localized based on the distribution of this dipole wave function. So we do the average in the QQ bar state first, then we average over all possible dipole size. Now I'm not showing row Forster here, it's really complicated. In similar way, we average in the MV model. Now there's slight complication is that those row in our cross sections are operator, they're color charged, they don't commute. But we said we use a classic source to average them. So we have to perform a symmetrization. Only the fully symmetrized expression can be averaged with a classic expression. One more thing is that in order to describe the data qualitatively good, we introduce a radius for projectile. So if we introduce a translational invariant source, then the projectile is infinitely large, which does make sense. Also, the V2 you calculate from the translational invariant projectile is monotonically decreased. That's which is not what data shows. All right, so for the target average, what we use is the so-called factorized dipole approximation. So you can think of, so we have this parameter, it's called saturation momentum. You can think of as a inverse correlation length. What it means is that when you have 4 Wilson lines propagating through your target, when the separation of 2 pairs is much greater than this correlation length, but the distance between the pair is smaller than this correlation length, then essentially they factorize into the product to dipole, which greatly simplify your expressions. Luckily, all of the Wilson-like correlators can be expressed in the following way. And when we use this approximation, we only get 3 terms, and we get a bunch of delta functions, which simplify the expression a lot. Now, one more thing is that how do we isolate the signal? So we can perform the symmetrization for the MV model rows. It turns out when you perform the symmetrization, the correction terms will reduce the power of rows. So when you symmetrize the row to the fourth term, you get a correction which is row to the row square term, which also contributes to the back row. Now, for the dipole, we do something similar, but we didn't know why we do this in the beginning, but we just feel like we should see what's the difference, how they look like. But then if you think about it, when you take 2 gluons emission from a source, the commutator will essentially give you a triple gluon vertex. Now, whenever you see one gluon emits another, right? So, which means that they prefer back-to-back instead of equally prefer back-to-back and in the same direction. So this is a simple physics explanation why this is a correction tool. This is the background. Now, after all the calculation, we can extract correlation functions to see if it actually give us the correct shape. Now, the first one, sigma 2, we plotted this back-to-back. Everything is good. For sigma 3, it is also picked at the pi, and everything checks out. Now, for sigma 4, it's non-trivial because we have to separate the non-symmetric part by the symmetrization procedure. And the result also shows that this non-symmetric part is picked at back-to-back direction. Now, those error bars are just from Monte Carlo integration. It's like 6-dimensional integral. But, we're not worried about the background here. Only want to focus on the signal. Now, after all the subtraction, the signal does indeed look like an equal amount correlation in pi and 0 direction. Of course, it's not like identical to data. You can see that in the peak, this is sharper than the data, and in the bottom, the signal is more flat. But we can still extract V2 from this result. I only have 4. Now, recall the definition of V2, right? For theorists, the most straightforward way is that you do the Fourier transform and you take a square root, which is not what was done in the experimental analysis. But they also check this quantity. If we assume factorization, which was an assumption in the hydrodynamics, then we can show, one can prove that these two quantities equal to each other, equivalent. Now, first we compare the result for V2 with the experimental data. We did 2 different range for the associated particle, and we plot the V2 results with respect to the transverse momentum of the trigger particle. And we did this for 3 different models. You can see that the HPT contribution is essentially control the shape of those of the V2, because after when the associated particle goes to 4 GeV, you basically include the HPT contribution from 2 to 4, which make this curve less steep than this one. And in Atlas analysis, they use 2 GeV. You can see that those 3 calculations are describe similar qualitatively, describe the data qualitatively, but quantitatively still a lot of uncertainties. Now, one more thing I want to mention is the factorization test, which is essentially see if the hydro assumption is correct. So this is so we still use from 1 to 2 GeV as the associated particle, but we did this for 3 different kinetic range for mono and dipole. We see that because of the HPT contribution is very sensitive to the momentum range, so essentially will control the location of the peak, and obviously does not have perfect factorization. Dipole is worse because dipole has more correlation because the dipole wave function. Now, the data has extra step to actually average the particles within certain momentum beams. So we did similar analysis, and we find out that we do this procedure. It makes it difficult to distinguish between different models. So this is my last slide. I want to give a quick summary. So we did an analytic calculation for the UPC and the rapidity to extract the particle correlation. But because the poor knowledge of the photon, we're not able to exactly reproduce the data. We just want to see what the correlation looks like in those 2 extreme limits. But we did see the qualitative behavior of V2, which is you go up first, then you go down. The further development is that you take into more effect to actually compare with data, such as final state effect and hadronization. And in other direction, right? If you go to large Q square, which is a work in progress, we can do this for EIC kinetics. Also, we only here focus on a fixed rapidity difference. So a natural extension would be consider the evolution between the 2 worlds. Thank you.
Right. I think it's up for Wish first.
Oh, very nice talk. So maybe, I am going to conclude about one thing. So I understand treating the target as empty source, with gluons. But if it's UPC, you just have like a low virtuality photon, and just like a dipole. I mean, should we sample color like an ND source for the dipole? Is this what you are doing? And if you are doing, is this a good approximation?
Yes, it's one of the case. So I did two cases for the photon. Right. One is NV, which is what you're talking about. Right. The other way is the dipole wave function.
So it's a very dilute.
Yeah, very
Right.
dilute,
Okay,
which is not really the case, but
okay, good.
it's it makes the analytic calculation doable.
Very nice talk. I have a question. The photons are linear polarized, right? Although it's only in transverse direction, but it's always linear polarized along the impact parameters. How does that reflect in your calculation? Because the spin is only one state, that means the electric field only always in one direction. Is that reflected in any of your calculation? I mean, I see you put the spin direction in, but it can only be in one single state because it's linear polarized. The other question is you mentioned above 2 GeV, there's a HPP effect. Can you explain intuitively why high momentum give you a big HPP effect? I will always think that HPP effect is a low PP phenomenon. So these are the two questions.
Okay, so the first question about the polarization of photon, I don't think that what you were talking about is very transparent in our calculation. So in our calculation, we just use this wave function, and then we sum over the two polarization.
Yeah, but there is only one polarization.
But there's another.
What I'm saying is the photon, there is only one polarization and it's
this one?
always along the impact
this-
parameter direction.
I don't remember that problem appears in our calculation, but maybe we should think about it. The other one is HPT. HPT is essentially delta K1 plus K2. So let's say K1 is the trigger particle, K2 is the associated particle. When you integrate with respect to the associated particle, it's gonna happen in every moment. But I did not compare the amplitude for HPT at different moments. So I don't know like what is the like how HPT contributes in low momentum or high momentum. What I was talking about is that in this figure between 2 and 4 GeV, because you don't have HPT, so it drops very fast. But here, because you actually integrate from 2 to 4 as well, you did include HPT.
But why would the HPP at such a high PP actually has an effect? I mean, usually the HPP effect we talk about is always very low relative to square. It's the 1 MeV, that kind of scale, 20 MeV, that kind of square. I'm surprised it has such effect from 2 to 4 GeV. Intuitively, I just cannot get the picture. But that's fine. Maybe your calculation is absolutely correct, but I just cannot turn my head around to see picture how that works.
Well, I don't have that intuition I'm talking about, so.
Can you try
don't know.
do it for one diagram, the stage BP diagram? Then you will be able to see.
Yeah, I do that practice.
I think Bjorn Have a question, so,
So the data, I think, is for high multiplicity events, right? And
Yeah.
you're computing two gluon productions. So how do you have a control about the multiplicity class that you're in? And the multiplicity dependence of the result?
So in the MV calculation, because we profile this mu squared as a constant times the Gaussian profile. So actually the value of this mu squared drops out in our sigma. So it has no multiplicity dependence.
So that would be a test if Atlas said, we can do like 3 different centrality classes, right? You would predict it's the same for. Right?
Yeah.
I have one quick question, you know, I know we're a little out of time. So when you actually calculate, V2, normally you can like break it up into a single particle distribution and 2 particle distribution. You obviously have clear 2 particle, so are you taking that into account when you do your calculations? Like calculate for 2 particles?
Can you repeat the question? I don't think.
So you can basically break up your V2 into a single particle distribution and you calculate that slightly differently and a 2 particle distribution. And I was just curious if you take into account both of those, like a single particle and 2 particle distribution in your calculating V2.
I don't believe so. We only do for 2 particles.
Okay, you don't have any single particle.
Yeah, I don't.
Okay, so then, thanks. All right, let's take one.